Hi, welcome to our presentations on the Traffy Fondue Resolution Time Predicting System. This is a complete end-to-end data science pipeline designed to solve a very real problems, telling the citizens of Bangkok exactly how long the complaint will take to fix. This project fulfills all the requirements of the data science and data engineering, cost demonstrating our abilities to handling big data, complex machine learning, and interactive visualization.
Let's start with the user experience. Currently, when our citizens report a problem like a pothole or a broken street light, they get a received notification, but then silent. They have no idea if it will be fixed in 2 days or 2 months. For our objective with this project is threefold. First, for citizens, we want to provide a transparent expected wait time instantly. Second is for the BMA. We want to help them optimize how they allocate resources across districts by identifying bottlenecks. And third is for data science. We want to build a pipeline that handles big data, advanced machine learning, and interactive visualization. We are working with a massive dataset, 787,000 real citizens complaints, spanning from August 2021 to January 2025 that represent over 3.5 years of actual city operations data. Let's dive into the engineering. We didn't begin with a clean spreadsheet. We start with a 1.06 gigabyte CSV file that containing raw, messy data. We face significant data quality challenges of the mixed Thai and English text in the same field. Second is about the inconsistent timestamp format, and most critically, the severe class imbalance. We found that almost 60% of issues are resolved quickly within a week, but there is a long tail, a critical 8% of cases that drag on for over 6 months. We also identified administrative noise. About 2% of tickets were resolved in under 1 hour, which represents the auto closure rather than the real work. We have to filter this out to protect our model. Because of the data scale, traditional tools like pandas were insufficient for the raw processing. So we have to build a robust ingestion pipeline using the Apache Spark. Our pipeline ingests the 787,000 raw records and filter them down to 500,000 complete cases. We specifically exclude the in-progress cases to ensure that our model learns only from the successful resolution workflow. The real magic happened in our feature engineering. We iterate through 5 different approaches, but I want to highlight the 2 techniques that unlock our model performance. First is the target encoding. Initially, simple label encoding failed us, so we switched to the target encoding, where we encode district by their historical performance. For example, like Din Dang average, it averages like 45 days to fix an issue, so the number 45 become the feature. This massively improved the model spatial awareness. And the second is the delta features. This was our innovation. We calculate the difference between a specific district speed and the city-wide average for that specific problem type. It tells the model specifically how much slower a district is compared to the norm for, say, like road repair.
We also couldn't ignore the text data. Description like ถนนเป็นหลุมมากครับ contains a valuable context. Standard tokenizers fail on Thai text because it has no spaces between words. We implemented a specialized NLP pipeline using the PyThaiNLP library with the new engine. We then use the TF-IDF to extract up to 3,000, extract the top 3,000 keywords and apply SVD or singular value decomposition to compress them into 15 dense features. This allows us to capture the complexity of complaint without blowing up the dimensionality of our model. And the result of this engineering effort, we transform a bloated 1 GB raw file into a highly optimized 167 megabytes Pocket file. That's up to 6.3 times compression ratio, while actually increasing the information density with 21 engineered features. This optimization allows our model training to run in minutes, not hours. Data science doesn't happen in a vacuum. We hypothesize that Bangkok monsoon season drastically affects repair time. That means you can't pave a road while it's flooding. So to test this, we implement a custom web scraper targeting the Open Meteor historical weather API. We wrote a script to pull daily temperature and precipitation data from 2021 to 2025, and we collected 1,280 daily records, exceeding the requirement of 1,000. Our analysis confirmed that repairs initiated during the raining season from May to October takes 15 to 20% longer on average. By integrating this external knowledge from API pooling, we engineered an "It's raining season" features that help the model adjust its prediction based on the time of the year.
Now, let's talk about the brain of the system. We didn't just train the one model, but we went through the rigorous experimental journey, training 5 distinct iterations. So in the first one, the model 1, we start with a simple XGBoost model using the level encoding. It failed with an R-square of the 0.1, and it was essentially guessing the average. The model 3, the one that have optimized, we have tried aggressive with the hyperparameter tunings using the randomized search CV, and surprisingly, this made the things worse. With the R squares around a 0.016, and because of the complexity of the model severely overfits to the noise of our training data. And our breakthrough came with the model 4, which we call our robust model. We realized the core of the problem wasn't just the hyperparameters, but it was the class imbalance. The model was ignoring the long, complex cases because they were statistically rare. And we fixed this with the hybrid resampling strategies. By oversampling the first one, we aggressively oversampled the slow cases by those taking around 100 days by 342%. So the model saw them much more often. Second is a sample weighting. We modified the loss functions, and we told the algorithm that we're getting long-term predictions wrong costs, which twice as much as the penalties at the short-term error. And the third one, recency focus. We prioritized the most recent 250,000 records featuring out the older data that no longer reflects the current city's operations. And using the strategies with an XGBoost regressor, we achieved the best results. With the R-square of the 0.6, which explaining around 61% of the variance into the resolution times, with the mean absolute error around 34.47 days. Now, the 34 days might have sound signs, but remember we are predicting the outcomes that range from 1 day to over 500 days. When we look at our stratified performance, we see the model is actually very accurate for the typical cases. For quick cases, around 0 to 7 days, our error is around 15 days. The highest is overall. Error comes from the unpredictable mega projects that take the years. But most importantly, our feature importance charts confirms that the hypothesis of the district's locations is the single strongest predictors followed by the complaint type.
Great. What a live demo from here. Well, firstly, we're gonna start with the left panel one. Yeah, in here we're gonna select the districts with the property for the inputs. So, for example, we're gonna start with let's select this. Then the sub-districts, we're gonna render some of the bang shan and the complaint type. Let's make it easy, and then just select a sample months. The middle of the year with the 6 months. So as we can see, this one is gonna be like the rainy season due to the Thailand season. And yeah, some of the common complaint descriptions is a น้ำท่วมขัง and they're gonna predict the resolution time for solving this problem. In here, the AI is predicted around 8.8 days, which considers as a quick resolutions expected. And okay, let's move on to the center part one. In here, we're gonna see the map as shown as a Bangkok. In this map is gonna matrix the average resolution days for solving the problems. Based on the filters with the constraints is PM 2.5. As you can see, the middle of the one, Bang Rak, the CBD centers, which considers at a high pollution areas. You can see that in here is going to be like the dark rate, which considers as user hydration for solving this problem in this area. And yeah, let's move to see this, analyze the insights. We're going to see the feature performance based on each of the metrics of the AI have rendered us. And here, some of the data sets to be and overview references in here. Yeah. And this is all our live demo.